Kia ora te whānau. I hope you're all doing okay, and I hope the sound is coming through all clear. Let me know in the chat if everything is working. And what we're going to do today is go through the slides and content for this week. So hopefully you can all hear me. Everything's coming through okay. Do let me know if there's any issues. Okay? So let's just check. No complaints so far, so why don't we make a bit of a start? By the way, if you arrive a little bit later on, please sign off in the chat so I know that you are present. And I'll tell you what our te rautaki i te wiki is. So we're going to cover static electricity today. And we're going to skip over lesson 3 because we'll be doing that when we have our Google Meet later this week. That'll be Friday, 5th period. We'll also cover some introduction to current electricity and looking at electrical circuit components. And the hope is that when we get back into the classroom, we'll let you have a little bit of a play around with all the electric circuits and make different types of circuits and sort of do some real inquiry as to how those different components mesh together. By the way, as we're going through the content for this week, you can fire off any questions that you may have in the chat. So just let me know how things are going, and if you've got any issues or if there's any partai, any questions that you've got, you can just fire them away. Okay. Sounds like we're coming through all clear, so that's positive. All right, let's dive into the first lesson on electrostatics. So the first thing that you would have done by looking at the slides is gone through this checklist. Now, if you click this, it'll open up a whole bunch of terms. And that's essentially what we're aiming to learn by the end of the topic. So there'll be some stuff in there and you're like, what is that? But by the end of the topic, you should be able to come back to that checklist and be able to tick it off. So don't stress too much if you don't know it all. So this little electrostatics vocabulary jumble was about looking at these different terms and seeing what you know and seeing if you can memorize it. It's often easier to memorize terms that you're familiar with. So there's some different ones in there around conduction and around charges of various kinds. So you can have a bit of a go at that. I'd encourage you to give it a little bit of a go, and you can upload a little photo of this if you'd like to, or just type in what answers you were able to get. This is just a little bit of a test for yourself. And see if you can match the meanings of those terms with those terms lists over there. There's also a little bit of a reading, right, that we need you to be doing. And there's some terms there on the slide that you want to be having a little bit of a look at, and then you can make little notes to summarize that reading. Now, summary is a really, really good technique for breaking down different topics as you go through. So it's always good to do a little summary of things as you're reading them. It helps you to stay focused while you're doing it. There's also a little simulation here, which hopefully you've had a little bit of a play around with. The simulations are really good. So PHET, run by Colorado University, and they're really great for just sort of understanding the basics, and this is looking at the fundamentals of static electricity. So even if you have gone through all the slides already, it would be useful to reinforce your knowledge to go and have a little play around with this. And it should work if you just go to that website that's there and have a little play around. So, what is static electricity? Well, static electricity is related to what we call forces of attraction, which is where you have different charges that are either similar, and so they repel one another, or opposite, and if they're opposite, they tend to attract. So the classic one is you get a little balloon and you rub it on your head, and what you find when you lift it up is that your hairs stick up and follow the balloon. And that in part occurs, and if we look at the previous slide, you can see that going on in the simulation, because the rubbing of that balloon causes a difference in charge across this balloon. So you end up with more, in this case they've shown it as negative charges here across the balloon, and that pushes away negative charges in here, but leads to essentially an attraction to the positive charges that are in the jumper or in your hairs, for example. And that's part of what attracts them together. So yeah, you can see sort of that example going on there. And that's basically all you really needed to go through. for that lesson, understanding those real fundamentals, that it's related to electrons. And once you've done that, there's one page of SciPad which you can do online. I'm aware that for many of us, we probably didn't bring our SciPads home, and that's okay. We've got it online there. Alternatively, you can, if you want a bit more of a challenge, have a go at explaining how a Van de Graaff creates electrical charge. And if we haven't ever seen a Van de Graaff before, we've got some slides later on which show how they work, but we'll have a little play around when we go back to class with one of these. Essentially, it involves generating some friction here, and that creates a difference in charge, and the negative charges migrate out to this little wand thing, and all the positive charges tend to gather around here. And if you get these two close together, that allows for those negative charges to hop across and cancel out these positive charges, which we see as a little bit of a spark, right? Now, for sparks to travel through the air, the difference in charge needs to be quite high. So that's basically how these things work, but there's a whole bunch of cool things you can do with Van de Graaffs. So we'll have a little play of that, and then once you've gone through either that or the SciPad page, there's some answers on the next slide for you. And if you really want to know how it works, you can watch this awesome video of Mr. Bill Nye going through it. Now, what we've done with the slides for this week is we've put these little, pause checkpoints in. Because we don't want you just diving into all of the content and blasting it out all at once. It's kind of stressful, and it's a good way to feel a little bit overwhelmed. So what we're trying to get you to do is take a little bit of a break between each lesson. If you want to, if you're watching this in the future, you're welcome to pause this video at this point, go and take a little bit of a break, and then come back and work through the rest of it. All right? So let's move on to the second lesson on static electricity. So this particular lesson covers some more detail here, and in particular looks at what voltage is and how that relates to current flow. So there's an opportunity here for you to just type out your answer without having a look at the next slide, but we'll go through the answer to this one. So static electricity is when electrons build up on something that doesn't conduct those very well. So a good example of this would be plastic. Plastic is terrible at conducting electricity. You can also be really bad at conducting electricity from time to time if you, say, wear some socks on a carpet, shuffle yourself back and forth, and then go out and touch something that's connected to the ground. You'll find you produce a little spark. And that's because you've built up a whole bunch of these electrons on yourself from doing that friction motion. You've picked them up from the carpet, and then you can release them all at once. Current electricity is when you have a flow of electrons, usually through something that electrons move through quite easily. So that would be like a wire, for example. When you connect a battery to a lamp or to a light bulb or to anything like that, what you're going to have is a flow of electrons through the lamp, which creates the brightness that you see as light. Those electrons then flow through the other side and then flow back into the battery. So that's our difference between static electricity, which is staying in one place, and current electricity, where you've got this kind of flow motion, right? Now, we talked about this just before. Like charges repel. So when you've got two electrons next to each other, they don't really want to be there. It's like this two south poles or two north poles of a magnet. They oppose one another. Opposite charges attract. So positives and negatives attract one another and cancel each other out. Kind of relates to our chemistry stuff that we were talking about earlier this year. In fact, it really closely relates to the chemistry stuff we were talking about earlier this year. So opposite charges attract, like charges repel. Now, relating to this, there are three main ways that you can induce static charge, right? Where you have all those electrons sitting on an insulator. And you can do it through friction, you can do it through conduction, and you can do it through induction. And we're going to break down each of those terms so you are familiar with them, because there will be questions on them at the end of the term, but also they're just good things to know, right? You'll come across them a lot if you do senior physics. Or if you want to be an electrical engineer, if you want to be an electrician, you want to be at all involved with circuits, you'll come across these things. All right. So friction's the one you've probably heard of the most. So friction is an opposing force, or a force that opposes motion. We talked about this when we were doing our forces topic. As you oppose that motion, what happens is electrons will tend to be transferred from one object onto another. The classic examples of this are the balloon rubbing on the hair. When you lift it up, you'll see that that causes that hair to stick to the balloon. That's because of the static electricity. But it also happens when you do this thing at carnivals where you have the kind of the mat that you slide down, that kind of like plastic slippy slide. You might have even done this at other places before. There's a whole variety of these sorts of things where you can do this. The classic little experiment you can do as well is get yourself a plastic pipe, get yourself some sort of woolen jumper or something, rub it up and down, and what you'll find is that you can float a tissue off the end, or a little piece of aluminum foil, which is quite fun, actually. So we might do that experiment when we go back to class. There are two other ways that you can induce a static charge. You can do it through conduction. And conduction is when something that is charged touches something that is uncharged. If you touch something that is uncharged and you're charged, you give your charge. You spread your charge across yourself and that object. That's the classic thing that happens when you accidentally touch something metal when you've built up a static charge. And you go, ah, right? That really hurts. It's because you've got this flow of electrons moving from one object to the other, spreading the charge equally across the two. It's also the same thing that happens when you're touching a Van de Graaff, but you're not grounded. And we'll have a go at this so you can replicate what's going on in these experiments later on. The third way to do this is induction. Right? Induction is different to conduction because you're not actually touching it. It's indirect. That's why we call it induction. It causes a local, or we will call like just a small difference in charges across an object. What's really happening here is if you were to charge, say, the comb on the right there, what you'll find is that the comb has a whole bunch of, let's say, negative charges on it. And as you bring the comb close to the piece of paper, what you're doing is pushing the negative charges on the paper towards the far side of the paper and leaving only the positive charges close by. Those positive charges are attracted to the negative charges in the comb, and so that causes the paper to rise up towards the comb. Now, when it touches the comb, that's when the charge gets spread equally across. But you can actually levitate pieces of paper by doing this. And if you happen to have anything plastic at home, I'd encourage you to give this a go. All you need to do this is something that's bad at holding charge, like a plastic rod or a plastic comb, and something that's kind of like frictiony, like a woolen jumper or maybe a woolen rug, and you just need to induce a charge by sort of moving it across, and then you should be able to find that you can manipulate things. Another good one to do this with is water from the faucet. So if you turn on a little bit of water, just so you've got a tiny little stream, you can bring the comb in and you'll see that the water will move according to where you put the thing that has that static charge. So that would be an example of induction. So friction, conduction when you're touching, and induction when you're indirect. Okay? So hopefully that's all making sense. I know that some of these concepts are pretty tricky, so if you've got any questions, you can fire them away in the chat or pop them into the comments. Okay, so our next thing we want to talk about is grounding. Right? Grounding occurs when you've got a difference in charge. Usually you've got a static charge that's built up, or you could be in the example of current, that could be the same thing. And then you connect it to a large source of charge. So essentially the ground, right? And that creates a movement of electrical charge from the object, which has built up a difference. And either it'll be those electrons move from your object here down into the ground, or the ground provides those negative charges that move up to the object that has just touched the ground. And a good example of this would be lightning. So with lightning, you get this sort of friction effect, which is caused by particles within the cloud frictionally rubbing against each other, which creates this difference in charge. That then creates a difference. It induces a charge on the ground, so you end up with this negative charge, say up in the clouds, and a positive charge there on the ground. And if that charge is great enough to overcome the huge distance that is at play here, which means there's a lot of voltage here, we'll talk about voltage in a second, that creates this lightning bolt. And actually what happens is a little bit of a tracer beam comes down, kind of slowly, and as soon as it makes contact with the ground, you've got all this ionized air, which provides a lovely place for current to flow through. So as soon as you get that first little beam from the ground touching, you get a huge volt coming straight back up, and that removes this difference in charge because you get a huge flow of electrons from one direction to the other, and that creates this balancing, this grounding effect that you have here. You can even have these effects occur between clouds. So if you've got two clouds, one above the other, you can actually have lightning bolts between two clouds, which is pretty funky. So yeah. So here we've got an example image, and it's your job to have a bit of a think about what is going to happen when this child on the left here touches the child on the right, or touches the ground, right? So if you want to, you can pause it for a second, and I'll reveal the answer in a moment. Okay, so in 3, 2, 1. So what happens is when this child touches the other one, you have a flow of electrons because you have a difference in charge. The child that was ungrounded had either a buildup of electrons or possibly the opposite. They had a whole bunch of positive charges in need of electrons, and as soon as they touch the person who is grounded, electrons flow through the ground, through the person, and into the person who was not grounded, and that dissipates the charge across everyone there, and that creates a little bit of a spark, which you will feel if you ever do something like this on the slide, and I'm sure you've had that experience before. Okay, we've got a few more things in here which talk about how this effect can cause you harm. So this is why we don't ever shove a fork into an electrical outlet, because you end up grounding. You end up taking all of the electricity out of the grid and putting it straight into the ground. It has to go through you, and because you've got so many electrons moving through you so quickly, that causes you a huge amount of harm. So don't do it. Okay. We've got some videos here of lightning bolts which kind of demonstrate that same effect, but here's another little whakaaro, right? A little thing for you to think about. So birds often sit on top of electrical lines, right, without getting zapped. They seem perfectly chill, just hanging out there. The question is why, right? There's a lot more current moving through those, particularly high voltage electricity lines, which sometimes happen from place to place. So see if you can pause and have a bit of a think. Reveal the answer in a few seconds. Okay? In 3, 2, 1. That's right, the birds aren't grounded. Right? There's nowhere for the electricity to go by flowing through them. So it takes the path of least resistance, which happens to be around / through the wire. So by the birds just chilling there, they're absolutely fine. If the birds, however, were to touch across the two wires, then there would be a bit of a kerfuffle, right? And sometimes that happens if you ever have a tree branch cross between two power lines or cause two power lines to touch. That creates a bit of a short circuit, which creates a huge flow of current between the wires, and that can be pretty bad news for any birds who are around. So with that, the only little wrap up is a couple of videos going over these things, and that brings us to the end of lesson 2. Now, lesson 3 we're going to skip over because basically that's just going to be a little quizzes or a Kahoot that we'll do during our Google Meet, but we're going to move on to our final lesson for today. Now, it's all the content that you need to do for this week. If you want to pause and take a little bit of a break, you can. Okay, our last lesson is on current and talking about the components that make up circuits, which we need to know in order to do what we'll be learning about next week, which will be different kinds of circuits. All right? Now, your first task today is to complete this page of your SciPad, right? And you can do that by accessing the online SciPad there, and the answers will be on the next page. There's also a little bit of a reading that we need you to do. And there's some questions in that reading talking about sources of current. So I want you to have a little bit of a go at that, and we'll make sure that those answers are available for you to have a little bit of a look at a later stage. Okay? Now, what you need to know about current electricity is current is caused by the movement of electrons in what we call a closed circuit. So the electrons can only go from one place to the other. In the case of a battery, you have a buildup of negative charges, and they move around to the positive side. Now, often we put something in the way, which we would call a component. And that could be anything that requires electricity to function. Something like a light bulb, a heater, a toaster, a kettle, could be whatever. Now, we have some diagrams that we use to make these things simpler. So we've got a little video that goes through some of these fundamental examples. Now, this might look a little bit tricky, but really all we've got here is a whole bunch of diagrams that we can use to make things easier when the circuits get more complex. The initial circuits we're going to show you are going to be pretty straightforward, and you're going to be like, what's the point? I could just draw a light bulb like this. But as soon as you get into more advanced electronics, you need to pair a whole bunch of these really complex circuits together. And we start introducing new ways for paths of electricity to flow, and so it's important to get these fundamentals down first. So what we'll be doing today is having a look at some of these different electrical components. So by watching this video, you should be able to figure out what all the different components are. A lot of them are just in that diagram there. But then you've got this diagram, right? And that identifies some of them. And I'll go through some of these answers for you. So you've got a bulb here, which we do with a little cross like this. And then you have what we call a voltmeter and an ammeter. Now, voltmeters measure voltage, which is how much energy there is going over a particular part of the circuit, right? Ammeters measure the flow, how rapidly, how quickly you've got that flow of electrons, right? A resistor is something that would get in the way of that flow, and it requires energy to pass over a resistor. Now, some resistors can be adjusted. They're what we call variable resistors. And we'll show you some variable resistors when we go back to class, but essentially it's just a resistor that can be turned up or turned down. That's the basics. So if you work through those, you should be good. There's a few more you need to know. A wire should be pretty straightforward. It's just a line. And then you have an open and a closed switch. All we do for that is we put two little dots, and we put a line between them, and we say the switch is open or the switch is closed. Now, the reason why we do that is because sometimes we want to look at what happens when we change a circuit. And a good way to change a circuit is to have a bit that is closed and then just open it, or to have a bit that is open and then close it, right? So that's why we include those in the diagrams. The last thing is a fuse. And if you've ever blown a fuse, you probably know what a fuse is. A fuse is something that responds to when you have unexpectedly high levels of either voltage or current. And they're there as safety mechanisms, right? So we'll talk about fuses now. And essentially all it is a really thin bit of wire in a tube. And if that thin bit of wire experiences too much flow, too much current, that melts the wire and that causes the fuse to be blown. Circuit breakers can do a similar thing, but they use kind of magnets, I think, to be able to do that effect. Which is quite funky, or they can use sort of circuit little measurement tools to automatically trip themselves. The cool thing with circuit breakers is they can be reset, so you don't need to stress about them too much, whereas fuses, once the wire's melted, you need to go and buy a new wire. So that brings us pretty much to the end here. There's those 2 pages of SciPad reviewing those different components, and you need to make sure those are done for this week. You can take a photo of those and upload those pages. But you'll notice that there's not actually that much work to do this week. There's just those various SciPad pages to do and a couple of notes to fill in. We're hoping that this isn't too overwhelming. I know it's a lot of slides, but hopefully this doesn't feel like it's too much. If it is, we can make adjustments for it in future. Okay? So that pretty much brings us to the end of all the content we needed to go through this week. And that took us a little bit less than 30 minutes. So I'm more than happy, because this will be saved, for you to pause the video, to go back to previous sections and review these things. You're also welcome to post comments, and I'm happy to go through and answer those, or you can bring your questions to the Google Meet for this week. So with that said, I'm going to hang on for a minute in case anyone has any questions, but all that I ask is that you have a relaxing rest of your week. You look after yourselves and your families. Maybe go for a bit of a hikoi, a bit of a walk around your neighborhood if you have the means to do so. Just making sure you're keeping your distance from people while we're still in level 4. And I look forward to seeing you on Friday for our Google Meet. So we'll chat again soon, I'm sure. But have a lovely rest of your week, team. Look after yourselves. Ka kite.